So I'll just turn to introduce our speakers now. We welcome Sacha Wright and Chris Beattie. Sacha has 18 years of experience working with aircraft design and certification, undertaking design changes to all manner of civil aircraft around the world. She joined 2XL in 2012 to create their in-house design capability. She is currently head of design for the company's Part 21J design org. And Chris Beattie started his career at Kinetic, working in test and evaluation of fast jet avionics and mission systems in 2005. But it was the opportunity to design and certify special mission conversions for aircraft which brought him to 2XL Aviation in 2014. And he is currently the Deputy Head of Airworthiness within the design organisation. So Sacha, Chris, I'm really looking forward to what you've got to say and to a really good, interesting lecture, and looking forward to some really good questions from the audience as well at the end. So I'll hand over to you.
Thank you, Nick.
Thanks, guys. We're just going to stop our camera and start sharing our slides. Okay, so good evening and welcome. Thanks, Nick, for that introduction. I'm Sacha Wright. I'm Head of Design for 2XL's Part 21J design organisation, and alongside my colleague Chris Beattie, our Deputy Head of the Office of Airworthiness, we're pleased to talk to you tonight about 2XL's project to convert and operate 3 King Air 200 aircraft for aerial surveillance for the UK Maritime and Coastguard Agency. Over the next half hour or so, we'll describe some of the highlights and challenges of rapidly designing, certifying and installing an advanced suite of sensors and communications onto a civil turboprop aircraft, taking questions at the end. So we'll start with a little bit of context and history on 2XL. In 2005, our founding directors, former RAF pilots, Andy Offer and Chris Norton, founded 2XL Aviation with the Blades aerobatic display team, the world's only aerobatic airline. In addition to flying their 4 extra 300 aerobatic aircraft in amazing air shows around the UK and the world, the Blades will take you looping and rolling and possibly vomiting in the skies on their unforgettable flying experience days. But with the global financial crisis in 2008, it led to a rapid need to diversify. Blue chip sponsors and corporate hospitality customers couldn't be relied on anymore to guarantee the future of the business in such testing times.
Sink or swim, Chris and Andy, what do you do? So what they did is they returned to that they knew very well, the defence and aerospace industry, and particularly test evaluation. So in addition to their extra 300s for the aerobatic team, the Blades, they got some trusty Piper PA-31 Navajos. And then they worked with other design organisations. We didn't have the capability in-house at the time to modify these to take customers' sensors and equipment airborne for test and evaluation in a proper representative airborne environment on an affordable platform at a much lower cost than you could afford if you were trying to put it on the target platforms like military fast jets or helicopters. The cost per operating hour for Piper Navajo is significantly lower than any of those, and it would allow those customers to come to us to fly their kit at early technology readiness levels, much earlier than they would otherwise wish to do, because it's more affordable. But also demonstrate the equipment to customers in the air. There are still passenger seats on these aeroplanes. You can take customers and show them the kit, and seeing is believing. And from that T&E business, the customers that we had there, we moved on to customers with managed service needs. So training for the military, we have cameras, sensors on the aircraft that we can emulate a UAV or a fast jet with a downlink, so we can do military training with these aircraft. We also then had civil customers for managed services. So we went from Piper Navajos and extra 300s to 2 Boeing 727 airliners. and we converted them for our customer Oil Spill Response Limited to act as oil spill dispersant spray aircraft. It's the first time that we know of that it's been done with a jet aircraft, and also the fluids, for the first time, they had to be treated as flammable fluids. So we have a very high integrity, double skinned spray system with, I think it's 14,000 litres of various spray fluids for breaking up oil spills on the surface of the sea. And to this day, we operate those aircraft, and we converted them ourselves with our in-house design organisation, which we developed over the time, in I think it was 2014, 2015, and then finishing up in 2016. So the T&E business, though, didn't go away. So that T&E business in 2016, we converted a King Air aircraft, so higher performance, pressurized fuselage, more comfortable, more power, more weight, with a large belly pod to help develop and demonstrate radars for our customer Leonardo in Edinburgh. And that business continues, that line of business continues, and the future looks like this in the bottom right hand corner. So that's a Boeing 757. We have a contract to modify that, and you might have seen press releases for Leonardo, again, as part of the Team Tempest initiative to develop a 6th generation fighter for the UK. And that'll fly with various sensors and systems for Leonardo to demonstrate those in a representative airborne environment before eventually making their way through to the Tempest fighter aircraft.
So in the spring of 2019, 2XL were awarded the contract to provide 2 King Air 200 aircraft for the aerial surveillance contract to the Maritime Coastguard Agency, with a 3rd aircraft contracted in late 2021. We're pleased to be able to tell you a bit about this project this year, as 2022 marks the 200 years of HM Coastguard, and we're very proud of our contribution to helping the Coast Guard save lives. Our focus is going to be on design, manufacture, installation and certification of the conversion. We're not best placed to discuss the operation of the aircraft, which is the domain of our special missions colleagues, a couple of whom I think are listening.
Yes.
So what does converting a King Air 200 to be used for aerial surveillance for the Coast Guard entail? Well, first of all, we started off with a pretty average looking King Air 200. There's space for 8 passengers plus 2 pilots, twin Pratt & Whitney PT6 turboprop engines, and a maximum takeoff weight of 12,500 pounds. From contract award at the end of March 2019, we had 8 months to take this regular looking aeroplane and build and install the first aircraft, with the second one following closely behind. And 8 months in certification terms really isn't that long. It's only possible to take on a challenge as large as this in such a short space of time with a really closely integrated team. We were really fortunate that our design, production and maintenance organisations, along with our pilots and sensor operators, are all located under one roof here at Doncaster Sheffield Airport, and we benefited massively from that, of being empowered to make decisions quickly and the ability to control our risks.
So when we talk about converting a King Air 200 for the aerial surveillance contract, what does that actually mean? So Sacha mentioned a normal King Air 200 has a max takeoff weight of 12,500 pounds. Now, if you fill the fuel tanks on a King Air full of fuel, as with many aircraft, you can't have the full payload with full fuel. And in fact, with the King Air 200, if you fill the fuel tanks, a standard King Air 200, you only get, you're probably going to get less than 100 pounds of useful payload. That's not enough. That's barely a person. Never mind all of the sensors we want to install. So the first thing that we would do to the aircraft is we go to the aftermarket modifications out there, and there are companies that have already on the shelf a thing called a supplemental type certificate modification to increase the max takeoff weight of the aircraft from 12,500 pounds to 13,420 pounds. So that's gaining us more than 900 pounds of max takeoff weight, and that means we can fill the aircraft full of fuel, and we've still got 900 pounds to play with, plus 900 pounds to play with for sensors, a sensor operator, useful stuff on the aeroplane, while still getting the maximum range that we can. However, this puts the aircraft from the normal category of a Part 23 in certification terms, Part 23 aircraft, to the commuter category of Part 23. And that brings with it certain requirements. So one of them is you have to have TCAS in the commuter category, so traffic collision avoidance system. So that means that TCAS, along with some other things, we had to do some communications, navigation and surveillance avionics upgrades to the aircraft. So new GPS navcoms, TCAS, ADS-B out to be fully compliant with all the regulation and also to be effective in the role. We also have to add sensors, and to fit those sensors we have the leading edge applications pod Maritime LEAP-M, which Sacha will talk to you about later. But that fills a large part of the belly of the aircraft, and there are already antennas there, so we need to move the antennas. It's quite busy in the parts that are not covered by the pod. So we relocate some existing antennas, and we also have to add new antennas for the new comms, nav and surveillance systems, as well as the mission systems that we're going to add. So within that LEAP-M that I just mentioned, the main sensor up front in the radome is a multi-mode surveillance radar, which we'll show you in a few seconds, right up there in the front of the radome. But then at the back, we have an electro-optic infrared turret, so a Westcam MX-15 in this instance. So cameras like you would see on your police camera action type TV shows flying around on police helicopters, we have such a sensor at the back of our LEAP-M pod. Also in the pod, we have a thing called an infrared ultraviolet line scanner. So that's a very special kind of camera for detecting and quantifying oil spills on the surface of the sea. So the aircraft, the aerial surveillance contract has a very significant counter pollution aspect to it to make sure that people who pollute the sea are held to account. We also have a search and rescue direction finding antenna system at the front. So this is a very interesting looking antenna which can accurately locate transmissions from emergency locator beacons, ELTs from crashed aircraft, people in the water with 4 or 6 megahertz capable emergency location devices. We have communications, so a normal King Air is going to have 2 VHF AM radios for talking to air traffic control. But our pilots and sensor operators need to be able to speak to people on surface ships, emergency responders, the Coast Guard themselves. So we've added a wideband communication system to the aircraft, and that involves additional antennas as well. We also have an automatic identification system. So much as aircraft have transponders, ships do too, and that's the AIS system. So we can receive the transponded locations of ships into the system and display them on the map on the mission system software that our sensor operator has. We can also offboard things from our sensors through a dual channel SATCOM with a high gain antenna, and that looks like a very large skateboard on the roof of the aeroplane, and that can beam up video to the satellite and down to the customer, the Coast Guard's control room or other government agencies. We have a drop tube. Sacha will show you that later on, but to save lives at sea, we might need to drop things to them, so life-saving supplies. So a hole in the pressure hull of the airplane to drop things out of. And finally, somebody has to operate all of this kit. So we've mentioned already the sensor operator. He or she needs a workstation to work at, and then all of this equipment has boxes behind it to make it all work. And that all sits in what we call a mission rack within the cabin of the aeroplane. So that's what we need to do. That's where we to. How do we do it? Obviously we start with the conceptual design at that kind of level, block diagrams and so on. But very early on, and this quote you might have heard, I think it was General Bradley from the Second World War, amateurs talk strategy, professionals talk logistics. To do this in 8 months is a massive logistical challenge. This stuff, you can't buy it from Amazon. Even if you could, you wouldn't get traceability to paperwork. It would never get through your quality system. You can't use it on airplanes. So you need to find a source of all the parts that you need to build this with. So very early on, to meet our timescales, we identified the parts we needed before we'd done the detailed design. And we have 3 ladies who worked full time to buy it all, to go out and find quotes for how much it's going to cost within the lead times that we have, and then to bring it all into the company. So Stacey, Rebecca and Becky worked full time for months to buy all the stuff we need. And then when it comes, you need to control it. It needs to be in a controlled environment. So we have stores inspectors. Some might call them storesmen, but that really undersells their role as the first line of defense for quality, to make sure that the bits we buy arrive are what they say they are, have the paperwork to support that, and are in a condition that's airworthy for making their way through to production or the maintenance organisation for eventually making their way onto the aeroplane. So this is a global project. The parts, the stars on the map here are the major items of equipment, not even every part, just the major items of equipment. And you can see it's from as far afield as Arizona and South Africa, and as near to home as Edinburgh. So I mentioned before, when we were talking about test evaluation, our good friends at Leonardo. They produce the Osprey 30 radar, which is at the heart of our system. And you can see here, hopefully the video plays and you can see it. But we're really proud to say that's, and it's pertinent because you're the Highland branch up in Scotland, proudly using a radar made in Scotland underneath our airplane. It's a really capable piece of kit, and it can detect even small targets on the surface of the water, which is vital for spotting small craft in distress or even people in the water. It's a really special piece of kit, and we're really proud that we've worked on the test and evaluation of this equipment with Leonardo on our King Air testbed, and are now a customer and a user of that on our ASV aircraft at the Coast Guard. So that's made in Scotland, but a big chunk of this is made right here in Doncaster in Yorkshire. So I mentioned before the workstation that the sensor operator sits at. And you can see the shell of that being produced literally, I think it's under my feet is the workshop where that is made. So where I'm sat now, right downstairs, is this workshop that you see in this picture. And there you see that the drawings that go into just assembling the top half, just the top half, assembling it. So not cutting the metal section, just pinning them together and riveting them together, as those drawings you see on that board there. So you can imagine the amount of design data produced and the amount of steps in the manufacture is immense. So it's a conventional aluminium construction, and that was a decision we took. We've done composite things before, but aluminium suited us because it's much easier to modify later if you need to drill more holes, if you need to make minor adjustments, or to even in future fit different kit. It was easier for us to work in aluminium and to control the timeline for this particular construction rather than using composites. The other benefit we have of being all in one roof is we can take things while they're in manufacture, and then we can take it in a controlled manner to the aeroplane. You can see here the aeroplane's absolutely stripped out for the modifications that we're doing, and we were able to take the opportunity. I think this was during a lunch break when the guys are not on there working. You can see Sacha there with her back to the camera, and Matt, who was a relatively new design engineer with us at the time, who led the design of the workstation. Really proud of what he achieved with this. They're trying it in for size. They're trying it on the airplane. We can do that. And being so integrated means that we can plan ahead to avoid mistakes and to make sure it fits first time when we've finished. And you can see as the construction continues on here on the left, we built the workstation effectively bare of all of its systems, nicely painted, ready for installation to the aircraft. And then we deliver it, literally passes through a door from the production organisation into the maintenance organisation, who actually work on the aircraft themselves. And we start fitting it out with all of the equipment that you see there on the right. So this is a bit further than halfway through production. It's still waiting for its screen and its fold-out table, but the rest of the systems are there. You can see we have on the right-hand side the direction finder, the SATCOM dialer, the radio, a video recorder, and in the bottom we have some power equipment, some network equipment, and a video encoder for sending the video from the camera off through the SATCOM. And there we're jumping well ahead to the finished workstation in service. You can see our pilot colleague up the front flying the aircraft, now a sensor operator colleague sat at the workstation, working the systems, the radar on the top screen, the map and the turret on the laptop screen, and an electronic flight bag on an iPad to his left, with his communications and his direction finder equipment as well.
Okay. So while the guys are bringing the systems together in the workstation and the mission rack inside the aircraft, we needed to accommodate the sensor heads outside of it. And the big three, the radar, the EOIR turret, and the UVIR line scanner, for us are all accommodated within our pod. Down the left-hand side of the slide, you can see our set of pods, starting with the LEAP, and then we have LEAP-R, which is for radars, and LEAP-M Maritime. And you can sort of see an evolution through them. LEAP-M took the existing radar pod design and integrated the EOIR turret and the line scanner. We'd had really good in-service feedback, as Chris was saying, from Leonardo on their engineering trials, that the LEAP-R radome shape and material gives really good performance with the radars. So we were keen to preserve that, but we needed to get the turret into a position where it had a reasonable field of view without the guys having to fly really odd patterns. So having an aircraft with the LEAP-R fitted, we did some rapid prototyping with some 2D cardboard attached to the aircraft. We were able to position it, look at different positions for the turret, the viewing angles, the ground clearance on the aircraft, and we had design, maintenance, sensor operators around the aeroplane looking at it all, and the lead pod designer, Rob, who's been involved in all of these evolutions of the pod, to be able to make a decision there and then of how we're going to take this forward. And he took that back to the CAD model that you can see at the bottom there to arrange the units and reprofile the back end of the pod there to give us the field of view that we required for the turret. And we have a sliding door as well built into the bottom of the radome there for the line scanner to see out of. At this point, we started doing lots of things simultaneously. Rob there rearranging the pod outer mold line and the units inside it and their attachments. The stress analysis for that all begins. The error analysis subsequently to feed into icing analysis, and manufacturing begins. Error analysis using CFD to provide us with air loads into the stress analysis, the airflow around the aircraft for icing analysis, and to give us some indication of drag and potential performance write-downs and indications for flight test. We're really fortunate to work with our aero guy, David, who's got lots of experience on mission system modified King Airs, who brings a lot to the party to be able to help us refine our designs and make them as aero efficient as possible whilst achieving the sensor performance aims as well. Production begin their manufacturing processes. Again, a big part of this for us was getting the materials in a critical timeline, so that they, not only the material but the composite manufacturers have time to lay up what is spoke, glass laminate prepreg and Nomex honeycomb core that's been tested for strength allowables, lightning compliance, radar performance. We built the first one and everything was great. And as we went to build the second one, the factory where we were buying the Nomex from burnt down. huge fire, leaving a really short supply and huge lead times. So having gone through the certification loop with one kind of material, we're then going back through that loop concurrently with the build to maintain the timeline, holding the risk of concurrent manufacture and certification on a material that we need to develop the allowables for. So our pods and our other kits for the aircraft are all built with a by our Part 21G production organisation, led by Rich, who oversees all of our in-house manufacturing and subcontractors, such as the ones that build the large composite assemblies for the LEAP M. On the slide, you can see the three main assemblies there of just the composite parts, the forward, aft and radome sections. We've got the pod upside down on the bench at the manufacturing facility, and then the right way ready to go on the get trimmed to the aircraft in our 145 facility.
So all the while that's going on outside the aeroplane to put the pod on, we're also working inside the aeroplane to fit out what must be miles of wire to join all of our systems together and to hook them up to the power system of the aircraft to get power. So what you see on the left there is our power distribution unit. So some of you might recognise circuit breakers there for every item of equipment. And also we have some relays, some contactors, because we to make it easier to certify, we make it so that if a generator was to fail in the aircraft and reduce the amount of available electrical power, the aircraft's essential systems get that power, and our mission systems, which aren't required for safe flight, are automatically shed without any intervention from the crew. And then on the right hand side, you see that installed in the mission rack that we mentioned earlier, along with our SATCOM system and some power conversion unit. And this is still in installation, so it's still waiting for the big blue box, which is the brains of the IR/UV line scanner for counter pollution work. And then just after that, on the right hand side, is the operator workstation, which we saw earlier. So it's a really invasive modification. So you can see the aircraft here. She's nearly finished at this point. She's painted. So this is at tea break when the guys have all cleared off, so I can take pictures without people being in shot and getting shy. And this is in our Part 145 maintenance organisation. And this photograph is taken from the corridor outside the design office. So literally, we walk outside where we're sat now, and you can see the progress on the aircraft. You can go down and talk to the engineers, all the issues, the sort of issues on the program that come up every day. And in this program, because we only have 8 months to do it, and it's a big job to do in 8 months, we need to resolve our issues in minutes and hours, not days, not weeks, and there aren't months left to do it. So you can see, I mentioned before, things have been manufactured in the workshop below our feet, and this is basically downstairs behind where we're sitting now.
So certification, there's lots of things that go into it. Structural analysis, area analysis, weight and balance, electrical load, equipment assessments, system safety, functional hazard analysis, ground testing, EMI. They're not as Gucci to look at flight testing. This is the glamorous bit that everyone's interested in. 2XL is an employer of quite a few ex-military pilots, and within that selection, we have two very capable and experienced Cat 1 test pilots, both ex-Navy. They're our preferred sort. And having access to that resource alongside our DOA Subpart P privileges for permits to fly at flight conditions enables us to develop a detailed and safe flight test programme meeting the certification requirements. We define that cert basis, which for this pod was slightly different from previous, with the change to the all at weight, bringing us to a later certification standard. We identified our means of compliance. We identified the test points that we'd need to show compliance to those requirements, and then developed an understanding of how to conduct those test points safely in an incremental approach. So as you can see here, we've got the white aeroplane. We've rearranged the antennas and that, but there's no pod on here, and the direction finder is not fitted. So we go out with a baseline heavy aircraft, and we the envelope of weight and CG, light forward, heavy aft, to find out how the baseline aeroplane flies. And then we add the lumps and bumps, the pod and the DF, and we check again. All those points on the envelope, incremental approach from a nice central mid CG to forward light and heavy aft, processing the data gathered and making sure before we go to the next test point that we're confident that it's safe to move on. We have a speed limit of 240 knots on the aircraft with the pod fitted, and there is a small effect on climb performance. But otherwise, according to the test pilots, it flies like King Air. And this is one of the reasons why the King Air is such a good platform for this kind of work. It's tolerant to the modifications, and as you've seen with the all at weight and some of the comms upgrades that we bought the STCs for, there's a lot of different mods out there for them, so you can start to piece it together. So we've got the aeroplane there, and you can see the DF and just quite what a protrusion it is. For the people interested in the aero, that has, because of the shape of it and that, a much more significant effect than you would anticipate to the pod. The proportion is not directly related to the frontal area. It's an interesting effect. And if you'd like to know a little bit more about civil flight test, our test pilot Chris Taylor has a book out, and Nick, if we can boost his sales, he'll probably even do a lecture for you. So flight test doesn't stop there. We need to be operationally effective with the aircraft in all conditions. The aero flow fields from the CFD get fed into an icing analysis, showing us where the water will gather on the air, where water will catch on the aircraft, and how that will accrete into ice shapes, not just on our protrusions, but also on all the unprotected surfaces of the aircraft. And from the certification perspective, there's a whole set of parameters of speed, weight, droplet sizes, hold times, altitudes that you have to run this analysis for to find what are your worst case ice shapes. And they're quite funky. And so we take this information and we get the sections and the shapes, and we get some foam ice shapes created for the aircraft, and sticking those on to not only our surfaces, but if you can see up on the fin there, the unprotected surfaces and the nose cone all get the same ice put on them, so that we are in the state that the aeroplane would be if it's been sat in that hold pattern for a while, including sandpaper on some surfaces to replicate the effects of thinner ice. And so we go out again. So having done the baseline with no pod, we've got pod, and now we've got with ice. And so we check all the performance and handling again, the combined effects and the potential impacts. And at this point, it is that controlled approach, knowing all the things that we found on the uniced aircraft, looking and building slowly towards those test points and creating ourselves a nice, safe environment and not negatively impacting the aircraft or the safety of our crew. And we managed to go to all the corners of the envelope safely and maintain that full range of weight and CG for the aircraft in both the normal and iced conditions.
But we're still not done with flight testing after all of that. Once we've established the performance and the handling effect on the aircraft of our modifications from the uniced and iced perspectives, we move on to noise testing. Now, every aircraft certified in Europe, for instance, has a noise certificate. And this goes down from ICAO, so it's an international thing from the International Civil Aviation Organization. But in Europe, at the time it flowed, we were within Europe and regulated by EASA, it flowed down to a regulation called Certification Specification 36, which is the noise regulation. Now, every extra drag and shape on the outside of the aircraft has the potential to change the noise of the aircraft. And it's really difficult to is that effect on noise. So the answer is to go flight test and measure it. Now, the ground equipment that you see here is the kind of the standard setup you need to measure that noise. And all of this is in support of a little microphone that you can see in the center of the picture, which we'll look at in a second. And because we have to do our testing within tightly prescribed limits for wind speed, temperature, relative humidity and pressure, we have to have a weather station. And we also need to dig a hole in the grass. So this is Sywell Airfield, and we've literally got permission to go and dig a hole in the runway. And you can see on the left of the picture, within our 7.5 metre exclusion zone, our grass divot from the hole. High-tech stuff. So there's our hole. Dr. Tom. So Tom is our lead on noise within the organisation. He really is a doctor. He has a PhD in aerodynamics. He's taken the team out to dig a hole in the runway and fill it with damped down sand and pat it down so that it has no cavities, because the requirement for this noise testing is so specific. And on top of that sand goes the required 40 centimetre diameter, 2.5 millimetre thick metal plate, which must be painted white. And a very particular type of pre-polarized microphone is then mounted in an inverted position with the microphone diaphragm exactly 7 millimeters above and parallel to the plate, and located 3/4 of the distance from the center of the plate to the edge along a radius line aligned with the reference horizontal flight path that the aircraft's going to fly over. So the thing to take away from all of this is this is a really particular setup. You must do it this way. It must be that exact, and a great deal of precision is required just on the ground part. Then you have to fly the aircraft over this, and that requires precision as well. So the aircraft is flown over the measurement point that we've just established on the ground to very tight parameters. So on the right-hand side of this figure, you see the blue box that we have to get the aircraft into. And that's a very small 10-degree cone from the vertical within plus or minus 20% of the calculated reference height over the measurement point. And that's basically simulating the climb out of the aircraft after taking off. And we have to fly over that measurement point, which is really difficult to do, 6 times within an hour of taking off at maximum takeoff weight. If you burn the weight down on the aircraft, you have to stop and fill up again, because a heavier aircraft is going to create more noise than a light aircraft. So on board the aircraft, we have a differential GPS system to measure that the aircraft has accurately achieved its position in 3D space to ensure and record that we were in the box when we make our noise measurement on that microphone on the ground. So all this technology is required, but we found that it's actually not too helpful for helping you get there. It's a difficult profile for the guys to fly accurately. So they were really good at it, and they found out ways to help keep hitting it first time, because obviously if you don't get your 6 points before you've burned down too much fuel, you have to stop and fill up and start again. So they found that actually they're always the best in the visual reference point. So I think it was a vehicle with headlights pointing towards their reference flight path would help them line up and reliably hit that precise point in the air to get the noise measurement at the ground. So it was brilliant piloting from them, good organisation and setup on the ground from Dr. Tom and the team. And we found that the combined impact on the aircraft causes an increase in noise of 0.1 decibels over the aircraft with just the all-up weight increase. So then we get a nice, at the end of all the certification, we get a nice new noise certificate from EASA, which has 0.1 decibels more than when we started after all that effort and all that precision. But that is absolutely required by the regulation.
And then we're on to one final piece of the puzzle. So we have a drop tube on the aircraft, as Chris said earlier. As part of the initial flight testing, we went out and we tested the performance and handling of the aircraft with the drop tube deployed, did some landings with the drop tube out. And those were flights that I actually flew on as an FTE. And it's a very odd feeling to open up a 6-inch hole in a pressurized aircraft and look through it and see the Humber Bridge. but that was the easy part. We did some more CFD to establish our confidence level that the articles dropped through the tube would separate safely from the aeroplane. And then Dr. Tom of noise testing fame and our trainee flight test engineer Albert developed the test plan and dropping procedures with our special missions colleagues to test something that's actually representative of how they will operate. And being part of an airline who regularly flies formation, we were able to get some of our trials colleagues involved in this test with a chase plane. And Albert flew on the chase plane and Thomas flew with one of our sensor operators on the King Air that you can see. And what we achieved was, hopefully if you can see this, is a nice orange whatsit, or a shape and mass representative lump falling cleanly away from the aeroplane. The sleeve that sticks out, helping us push through any kind of boundary conditions and removing any potential problems with it, and training back, and as you can see, hitting all of our antennas that are on at the back end of the aircraft there behind the pod. And we'll see that one more time because it's just my favourite video.
And hopefully with the bandwidth, some of that will come through and you'll see some of that action, because I know it won't be as smooth as it is on our screen.
And so into service. So with all of the various analysis testing done, our STC substantiation submitted to the authorities, finally we get our certificates back and the guys can enter into service. And as we speak today, we have the drop tube capability, we have 3 aircraft all modified and available and in service, providing support to the Coast Guard.
Yeah, operating 24/7, as you can see out the window there with the moon. So what does the future look like? So the future looks a lot like this. So the ASV contract was a reasonably short-term contract. And the Maritime Coastguard Agency was looking at letting a new contract for 10 years running from 2024, covering its rotary wing search and rescue helicopters, as well as the fixed wing aerial surveillance parts that it was letting out. And we were very fortunate to be part of a consortium with Bristol Helicopters, who are the incumbent for the rotary wing side of things. And we're very pleased that in, I think it was July this year, it was announced that we had won the contract for what's known as SAR2G, or the second generation search and rescue contract for the Maritime Coastguard Agency. So the future is this team that you see here. So 2XL modifying and then operating an expanded fleet of bigger, more capable King Air 350 aircraft, in addition to some of the existing King Air 200 aircraft from 3 bases around the country. In addition to Bristol Helicopters with their Sikorsky S92 helicopters that you see here, along with their Augusta-Westland 189 helicopters, and I think some AW139 helicopters as well, and also unmanned aircraft like the Schiebel S100 camcopter you see at the bottom of the picture. So we're really excited that by 2024 we'll have converted 4 more aircraft for this customer. So there's a lot of hard work going on now as we speak. So that's a lot to do between now and November 2024. But we're really excited and really pleased that by the time we've come to do this lecture, we can say that's the future and that's where we're going. So that brings us to the end of our prepared remarks, and we'll turn the slide.